A mass of 2 kilograms is attached to a spring which is stretched 10 centimeters away from its relaxed position. The mass is released and starts to oscillate with a period of 2 seconds. We are asked to find the function that describes this oscillatory motion and sketch its graph. In order to do this, we need to know what mathematical function will describe oscillatory motion, and we need to be able to identify basic properties of oscillatory motion. The first property we can find is the amplitude of the motion. This is defined as the maximum distance away from the equilibrium position, and in the case of this mass on a spring, it occurs first at time t equals 0 when the mass is stretched that 10 centimeters. So the amplitude is going to be equal to 10 centimeters. The next thing we want to find is the angular frequency. This is equal to 2 pi divided by the period of motion. We are told that the period is 2 seconds in the problem statement. This means that the angular frequency is then equal to pi radians per second. The mathematical functions that describe oscillatory motion are sine and cosine, which have the definitions that at time t equals 0, sine of 0 is equal to 0, and cosine of 0 is not equal to 0. Looking at our situation, we see that at the initial time of t equals 0, our mass is 10 centimeters away from its relaxed position. That means that x of t is going to be non-zero, so we're going to want to describe our motion using the cosine function. Putting everything together, we can write the equation of motion as x of t equals the amplitude times cosine of the angular frequency times time. Plugging in the numbers we found, this comes out to be 10 cosine of pi times t. For graphing the function, we draw a cosine curve, which has a period of 2 seconds, meaning the peak-to-peak distance is t equals 2, and has an amplitude of 10 centimeters, meaning the distance from this equilibrium position, x of 0, is 10 centimeters. Looking at what the mass actually does, it starts at the initial time before it's released at 10 centimeters, and it oscillates from 10 centimeters away from the equilibrium position on one side to 10 centimeters away from the equilibrium position on the other side, and this motion then repeats itself.